We're going to be discussing today a paper on multi-token prediction. This research was done primarily at Meta, although it was also done together with some academic collaborators. The paper itself, it reads very, very much like an academic paper, which is, I just wanted to point that out. It's very rigorous. It explains some of the science and the philosophy behind the experiments and the considerations that they have. So that's just something to keep in mind when looking at this paper. It's much less of an engineering paper and much more of a scientific paper. Okay, so let's actually just jump straight into it. So the basic big result that there is inside of this paper is that instead of doing next token prediction, which is of course, you know, the whole game that there is for large language models, you can actually do multi-token prediction with claims that you can improve the speed of inference and improve various types of tasks that large language models can do, such as summarization, mathematical accuracy, code completion, which were the three major tasks that were tested inside of this paper. The authors, yeah, so the main thing that the authors point out as far as the limitations for next token prediction are that next token prediction, as I'm sure many of you who have played with large language models over here know, is highly inefficient. The longer your context is, and the longer you want a response, the more inefficient it is to be predicting with the next token prediction. It identifies only local patterns. So this is where you get the problems like the loss in the middle problem or the needle in the haystack problem, where you lose a lot of the context that has come before if the context is very, very large. Although there are some techniques to try to mitigate some of those effects, it's still, next token prediction is still a very, very it's a technique that recognizes very, very local patterns. And this is also why, because next token prediction is very, very much just recognizing local patterns, it fails in many sequential or reasoning tasks. It's not looking at larger landscapes of semantic text. It only really truly looks at whatever is the most likely next token based on some distribution. And yeah, related to that, it overlooks some hard decisions. All of these are pointed out inside of the introduction of the paper. Lastly, to be able to have next token prediction to be so effective, and the reason why large language models truly exploded is because of the way to make it to be so effective is by using orders of magnitude more data in order to be able to make very accurate and good next token predictions. Without the orders of magnitude of data, or I mean, there are, yeah, it actually does lie into orders of magnitude of data. You do not get next token prediction to work so well. So what the authors over here propose is a different way of doing. It's a different way of doing token prediction. I'm going to switch over to my iPad. So we're going to just jump over here. And again, I apologize for any technical difficulties if I'm flipping between different mediums. Right. Okay. So So I want to write so that we can just all be pacing on the same page. Oh, look at that. It worked. I see. Okay, it worked. Do you guys see it? My screen is still being shared. I'm not sure why I was having this glitch earlier then. This is perfect. All right, great. Okay, wonderful. It managed to correct itself. Excellent. All right, so great. Okay. So the main idea about training a model for next token prediction is that when you're training this, whenever you're training this model, what you're doing is you're computing what is the cross entropy multiplier, which is this loss function. Usually it has a negative sign so that you minimize rather than maximize. It doesn't really, the negative sign doesn't really matter so much. But you're basically predicting based on some parameterization what the next token is going to be based on a sequence of previous tokens. So this is going to be a sequence of previous tokens. And xi are all going to be tokens. And so what you want to do is you want to maximize L1. And there are many, many types of optimization techniques that are that you can do to be able to maximize L1. And so, of course, like, when you're looking at large corpora of text and trillions of tokens of data, of course, this slows down a lot of the training because you're really going to be predicting one token at a time. Okay, so what do the authors propose instead? They propose that instead of maximizing for one particular, can I get rid of this? Is that possible? No, cannot seem to get rid of that. Apologize for the glitches. This did not happen the last time when I was doing this. Okay. All right. Okay, so instead of maximizing just for the next token, rather let's set up a loss function where we're going to be computing the next n tokens. So we're going to be maximizing xt plus n through xt plus 1, granted xt, the first key tokens. So now we're going to be looking at a sequence of tokens. Now, I'm going to just pause here before we actually go into how we can train a model and compute this. Because a priori, of course, every single way that we're training large language models, there's nothing that restricts us from just doing this in our training of a single transformer. And in some ways, when we're talking about tokenizers, we are already implicitly doing this. So if you remember, for tokenizers, there are multiple ways that you can tokenize a piece of text. You can do it at the byte level, at the subword level, or at the word level. When we're looking at text that is at the subword or the word level, what we're effectively doing is some kind of a dynamic version of setting up these sequences for the next token prediction, if you consider the tokens to be at the byte level. Of course, it's a dynamic version because the lengths of words can vary, the lengths of subwords can vary. But in some sense, we train it, we hard code what are the lengths which are going to be associated to when we tokenize a given sentence. Now, people have studied, and I just want to really just dispel this whole notion of just doing this. Without all the techniques that are going to be developed, just by taking this to be your loss function and then just running everything as it is. I want to dispel that that's not going to work. And the main reason that that's not going to work is very much related to this tokenization problem. When people have studied many things with the tokenization problem to be able to try to find the optimum size of tokens that are going to work in order to be able to train these models well. And so if you have if you have too long sequences, you do not train a model well at all. And this has been studied very well. So if we're looking at tokens to be at the word level, then what we're looking at over here for this part that is starred, we're looking at something like a sentence. We're looking at multiple words. In particular over here, n different words over here. So whatever your length of n is. And training a model to predict on that large macroscopic of data, it breaks the model's predictive capabilities apart. So it might work if we use, I'm just going to throw this thought out there. This has no substantiated claim because no one has ever done this experiment. It might work if you are going to be training on orders of magnitude more data than what we're training on currently. But at the moment, you cannot do that. Okay, so then what can we do instead in order to be able to get this? Now, note that the probability is only conditional on the first t elements. So mathematically, this is the same thing as if we break this down into a sum of probabilities where what we're doing is we're predicting the t plus ith token based on the first t tokens. So we changed the problem now that we're going to be predicting one token at a time. But we're going to now be predicting one token at a time in parallel. So so basically now our loss function for the next n tokens becomes n loss functions for the next one for each of the next tokens. So let's take a look at the paper to see a little bit of the architecture over here and what they're doing. So the architecture for this is over here on the very first page in figure 1. So over here they show it with 4 heads, meaning that the n over here is going to be equal to 4. And what they're doing is, so you have your inputs. You have your inputs, you have your shared trunk. The shared trunk is going to be your how you're going to be embedding the words. So you get your embeddings. Now you're going to be passing it into the transformer heads, and you're going to be passing. You're going to be running n parallel transformers at a time, each of them doing a 1 token prediction. But the first transformer is going to be doing the next token prediction. The next transformer is going to be the 1 token out token prediction, and so forth and so forth. And so you should think about this as like you're chunking your text into sequences of n, and you're moving that window of n, and you're going to be doing every nth token prediction. Yes, Harpreet.
Yes, I think you, I don't know, maybe you're gonna cover it later on, but is it that the transformers are truly in parallel, or there's some sort of cross attention between the transformer blocks?
Yeah, that's a good question. Okay, so there's a little bit, is there some cross attention between the transformer blocks? No, they're actually in parallel. They're actually trained, they're trained separately. And that's actually something that's critical, that's inside of the appendix, that the weights of one are not going to affect the weights of the other. That being said, though, there's no way, there is some sequentiality. So for that, we can jump over to figure 2, which is how they end up training it. They really train one head at a time, even though each of the transformer models are trained completely separately. So the weights are just not going to affect each other. But you're going to be training the first head, which is going to be the next token prediction. You get back the next token. And so actually what you're going to be computing, because there's no way that there's a missing token, right? All of this is sequential data. So if you want to get the second token or third token or the fourth token, right, you need to know what the previous tokens were. So like what you're actually computing is going to be always the next token. So for this t plus I granted this, what you're actually computing is this granted x hat t plus I minus 1 through x hat t plus 1 and the rest of the sequence. So that is, to my understanding, the degree to which the different transformers are interacting with each other. There are other ways that they did try to, yes, Sir Jansh.
Can you just explain this statement that you've written?
Yes, okay. All right. So a priori, all right, so granted, okay, so what's the nice thing about next token prediction? What's the philosophy by which, like, we do next token prediction? It's basically granted some sequence. What's the, how do you maximize the probability of what what next token would maximize this probability, right? So as long as like, you have granted like, the previous sequence, it's easy to compute and it's easy to know what the next token is going to be that maximizes that probability. Now, if you are going to be skipping a token, so let's just say like, you have tokens, you have the sequence A, B, C so far, and then over here for our next token, right? Like we're going to be, this over here is going, predicting this is going to be xi plus 1, granted xi through 1. And then predicting the one after that is going to be xi plus 2, granted xi plus 1, sorry, xi to 1, sorry, granted the first I. But over here, what we have in order to be able to predict this one is a gap. So unless if we're going to be computing this one by looking at literally every single possible token that can go there in order to be able to like maximize this. So in order to be able to compute this, like truly, truly on the nose, you need to have some notion of what's going to be over there. And so unless you're going to be computing it by going down the entire tree, which is very, very computationally expensive, and then, maximizing this granted every single possibility for this, you're not going to be able to get a good result. And so what they do is they actually do the sequential computation for this, where they first compute what the next token is, and then they compute this or approximate this by knowing what the prediction for that token was. So in some sense, you're still doing next token prediction when you're setting up the system. The only thing is that you're only training each of the parallel models on the nth token. So you're not training it completely and totally sequentially. You're not training it on every single token. So the first model is only going to be trained, like, if you cut up your text into, tokens of length n, the first model is only going to be trained on the ones at position 1. The second model is only going to be trained on the ones at position 2. The third model is the ones that are trained on position 3, and so forth and so forth. And so in this way, you break up the computation into n different models. And there's a way that, I'm not going to go into this, but there's a way that they optimize it, even though it is a sequential computation across these parallel models. All right. Are there any further questions about the setup for the architecture? Yes.
Sorry, I missed this. What you just said you wouldn't go into. Where's that in particular in the paper, just so I can reference
it's
back?
in section 2. So the memory efficient implementation for inside of the methods.
Cool. Thank you.
Yeah, and then they like figure 2 explains that a little bit further. So figure 2 is the one what is corresponding to that. Okay.
I have a question.
Yes.
Wait, so long ago, I remember just having fun almost on a phone, like auto completing something, like just type 2 words like I have, and then what's the first one that auto completes? Pick that. Then what word comes after that? Just for autocomplete, pick that, and just keep going and have it just pretty much build its own sentence. And it would never make sense. It would always just be like an absurd non-sentence. With this though, with it always like selecting for what's going to be in slot 3 and what's going to be in slot 4, would that mean like if I were to play the same game, it would at least be grammatically correct? Like it wouldn't be.
That's not guaranteed. That's actually never guaranteed for a large language model that you have something that is grammatically correct. There are corrections that people do in their models for, after you predict some amount of the output to like correct if there's a grammatical error, but it's not guaranteed because it's being trained on so much data. And we assume that the vast amount of data that it is being trained on is most of it is grammatically correct. The probabilities of something as being the next token that is being predicted being grammatically correct is higher. And it's sometimes so far higher. So then if you set your temperature to be quite low, then and you skew your probabilities to be spiked as like a delta function, then you're going to be able to get things that are grammatically correct with a very reasonable amount of a certainty. But there's no guarantee for large language models. A priori, there's no guarantee. So everything that makes things be perfectly grammatically correct are post hoc corrections to what are the outputs.
Okay.
Yeah.
So I have one question. So you said like we'll have models trained based upon like the number of tokens, right? Say 1, 2, and like say 3. So how AI knows what to fetch next? So like if I say I like to complete next, how it will know that it has to fetch or have had like how it knows like how it chooses the number of tokens for the next sentence.
The total number of tokens, or the
next word.
Are you asking about like the total number of tokens to like complete a sentence, or are you asking about just how it chooses the next token specifically?
The next word. So because like we have already trained on the based on you said like the number of tokens. Say if I just put I, then it's a single token. So next can be anything, right? So there are n number of probabilities. So how it is happening?
Okay, right. Okay. So when you train a model, on the entire vocabulary, you get a distribution. So the model is like you get a probability distribution on the vocabulary. And so this is what the model is being trained for. So that given an input sequence, what's the probability distribution on the entire vocabulary for the next token? Now, then this depends on a combination of your parameters for the temperature and for top P, to be able to figure out what your next token prediction is. Now, if you set your temperature to be equal to 0, then at least in theory, and I'm going to say like in theory, you would get something that's a delta function. So the temperature is going to take your probability distribution and it's going to be doing some kind of a skew on your probability distribution. So the higher your temperature, the more it's going to be flattening it. The lower the temperature, the more it's going to be spiking it. And it's going to be spiking it at the points where you have the highest probability. So as long as you have like a single token that has the highest probability, then it's going, if you set temperature to be equal to 0, then it's going to 100% guaranteed to predict that. Now, this is in theory. In practice, everything is going to work a little bit differently because there's all sorts of noise and error that gets added in, not to mention rounding errors. And so it does happen quite often that you do get a single token that is like the clear highest probability that if you set your temperature to equal to 0, you're going to get, exact prediction. But the more you quantize things, the more you try to be memory efficient, the more complex your sentences are, the more likely you might get like multiple spikes. And then there's going to be a little bit of coin toss at that point, to be able to do the next token prediction. When you set temperature to be equal to 0. When temperature is higher, then it's a combination of like top P and temperature. And so top P is, you can kind of think of it as like, kind of like a sampling technique. You're not going to be sampling from the entire distribution. You're only going to top P and temperature, like you set your temperature a little bit higher and then you vary your top P. Think about it as like, sampling, doing a random sampling from some subset of your distribution. Usually like a very, like your top P kind of like, tells you like which amount of like, the distribution that you want to be sampling from. And again, you can set your top P so that you include the entire vocabulary set. And you can also set your temperature to be like, effectively infinite, in which case it's going to be doing completely and total random predictions at that point. And so as far as like, like the generative capabilities, and as far as like, being able to generate new types of responses and these so-called like creative types of responses, it becomes a game of like, changing these two parameters, the temperature and the top P, to be able to understand which part of the distribution you want to be sampling from. And you cast your net a little bit wider, basically, like by changing these two parameters. The important thing to note about it is, of course, as I think it was Philip Crawford who was asking the question about, the grammatical correctness. The higher your temperature, the larger the distribution sampling that you set for your top P, the more likely you're going to be getting. In fact, like you're going to be guaranteed to be getting like grammatically incorrect and just completely random nonsense at that point.
Thanks.
All right. Any further questions?
I have a question.
Okay.
Yeah, so say like we did 2 token prediction like in parallel, first and second, and after the first prediction, the second does not make sense at all. But the second, we did not have that information while doing the second prediction. So like, does the paper talk about how to deal with such situations, or?
So we do have that information for like what was like predicted, right? Because like the way that we approximate this, right? This was the whole thing. Like it's very hard to like figure out like how to maximize this with a gap, but that's also another reason why we would do the computation sequentially. So when we're computing this probability over here, this gap, we're actually going to be taking what the output of this is. So we're actually going to be computing this. Okay. So we do have the information from the previous thing. It's just that so like if we look at the paper, right, like then we follow the flow like on the first head. So when we predict the first token, we go into the first head, so the first transformer. We predict that token, we put it back into, we embed the whole sequence. So this is the shared trunk, which is where you embed your sequence. And then we take that embedded sequence, we do the next token on the second head. And then we do it on the third head, the fourth head, or however many heads that we want.
Okay, thanks.
Yeah, it's just that each, again, like the basic idea is like you take your entire text and you chunk it into sequences of n tokens. And the first head is just, always going to look at the ones in position 1, and it's going to be trained on the ones in position 1, second head, position 2, and so forth and so forth. So you break up the computation. You're not going to be training it on the entire thing. You're only going to be training it on every nth token. And the weights, as far as I understand, they're not going to be affecting each other. But there are some other architectures that they do consider in the appendix, where you do have some kind of like causal relations. And we can look at the appendix at the end and look at some of the figures and some of the results that they have over there for some other architectures that they considered. So the last thing that I want to point out is the last thing about the architecture that I want to point out is so there is a way that they make this to be a very efficient training paradigm, but another thing that I want to point out is their decoding procedure. Because now they have multiple, so like the decoding procedure, meaning like, what's going to happen at inference. Because right now, like what's happening at inference is, of course, like, you're decoding always like at the next token prediction. And so what they end up doing in order to do multi-token prediction is something that is not actually their invention. This is in this paper. Well, in these two papers, it's blockwise parallel decoding. And I'll drop this in the chat. So this is the decoding procedure that they're doing. Okay, so how does the decoding work? So for blockwise parallel decoding, it happens in 3 steps. So the first is the prediction step. So remember, these models were trained on predicting the jth token. And right. So what they're doing is they're so in theory, right, like what we're trying to get is whatever this probability is. So when you are doing your prediction, you are actually going to just, you're going to be running all of them in parallel. So you're just going to be predicting a token. So you're going to predict your ith token as the minimum I'm gonna write this a little bit differently. I'm gonna write this so that it parallels the way that we wrote things before. So for the ith probability, what we're going to do is we want to let's talk about just maximizing probabilities. Let's not add in like too many like pieces of notation. So what we're doing is we're just going to be choosing the so granted everything that was predicted up until the jth, sorry, give me a second. So let's say I used T before, right? Let's use T. That was a notation. Okay, good. All right. So for each of the heads, so for the ith head, you're just going to be making a prediction for this. So make a prediction for one token in the sequence. Granted the first T tokens. Then what you end up doing is you want to verify that this prediction actually worked. And so you do this. So let's just say like, you have n heads. So that means that I ranges from 1 through n. So now you're going to verify that these predictions that you're making are actually good predictions. So this is the point where you're going to be finding the largest n hat such that if you predicted, we're going to call the prediction to be y hat t plus I, right? Because, yeah, so this is going to be the prediction. So you want to find the largest n hat such that y hat t plus I is going to be equal to, if you look at just the first head, the one that did the next token prediction, so the first token in the sequence, that this is going to be the same thing as if we're going to be maximizing the probability of the first head granted the concatenation of, sorry, I meant to write that as an I over there. Granted the concatenation of t plus I minus 1 through t plus 1, and of course the original sequence. So what we're doing, so let's really break down like what happens at this verify step, and let's really like go through this like really step by step. So when we look back over here in this diagram, when we're doing prediction, so when we're doing decoding, so when we're doing inference, we're going to have each of the heads just predict a token. Now we take those tokens and we're going to go sequentially by using, and we're going to just use now the first head, the one that did the next token prediction. Now, what we're going to do with the next token prediction is we're going to start by, so we predicted now like n tokens but from each of these heads, and let's let n to be equal to 2 for now. So now then we look at the first head, and now we have the predicted thing. And now granted, the original sequence plus the predicted sequence, we're going to now predict the second token. the next token that follows that original sequence. Because the first head was always trained on, strictly the next token, strictly like, very much like, the next token thing. And then if it matches, if it actually is equal to, like the thing that we predicted on the second head is the thing that maximizes this probability, then we're good. That means that we've succeeded, that this is the token that we would want. And then we do this for like the third head, for like the first two, the fourth head with the first three, up until we fail. And so in this way, we're predicting multiple tokens at a time. And we're really like verifying with respect to the first head, how well this prediction works. And so then the last step, of course, is that, you accept. If it works, then you extend y hat with you extend yt. Ooh, sorry about that. I meant to. You extend yt plus 1, t through 1 with yt plus I, t plus n hat through yt plus 1. Yes, Mark.
So I'm looking at figure 2 out of the blockwise parallel decoding paper. I don't understand on the last chunk under predict, they have that arrow that shows reused. Can you dig into that? I just don't get why that's used.
Okay, figure 2. Okay, so
Yeah.
okay, so I will say I also don't know. I did not read this part of the paper. The part that explains what the prediction is section 3, and it's figure 1.
Gotcha.
Yeah, so there's
It's no sweat. I didn't want to derail you.
no, it's good. I just did not read this part because the part that the paper references is the blockwise decoding in section 2. There are multiple, and the paper does reference it. By the way, there's like multiple ways that you can do like blockwise decoding, where you run predictions in parallel, and then do a verification step. And the verification step is apparently supposed to be much cheaper than like the decoding step. I think that requires like a little bit more to like, jump into and like run into to really understand that. Yeah, I apologize. I did not read this entire paper because the part that was needed was blockwise parallel decoding, section 3. But if you want, I can get back to you. We can chat on, like the Tarot Slack channel, and then figure out some of this, what's going on in figure 2 over here.
That'd be great. Thank you.
Mm-hmm. Okay. Okay, so you're doing these like parallel decodings now, and so you're getting back. So you're getting back only those that are going to be so your decoding strategy is going to be whenever it's going to be verified by the first head. Okay. All right. So this seems quite complex, and it's almost miraculous that it works like so efficiently that it does, because there's so much that is being involved, and there's so much memory usage because you're running multiple transformers at once, and there's a lot to say about various types of optimizations that they do, especially for memory usage and all of this. Right. but I think like the big question to ask is the experiments that they set up, why they demonstrate that this is actually an efficient, this is actually a good method to improve the performance of large language models. And so I want to dig into some of those in the remaining time that we have, and to just break down what the experiments are, and also to break down, how this could be useful on a practical level, and kind of some things that I see as like, things that could be like things to explore, things that are next steps, and so forth. So the experiments that they have, there's multiple questions they're trying to answer, and this is all in section 3 of this paper. So the first thing to note, and what I really appreciate about this paper, is that they're actually quite honest about where they're not performing well. So multi-token prediction techniques like this one are not new. Like these other papers that I have over here, and I'll drop all of them in the chat at the very end. These other papers are like from back in 2018. And people have been trying with like different types of like parallel architectures to be able to do multi-token prediction, but they haven't been getting good results. And a lot of the reasons that people have not been getting good results is because the models were just too small. So one of the first things that they're experimenting with is just code completion. And so they're training these models from scratch, only on code, only on very like perfectly curated code. And what they do is they look at models ranging from 300 million parameters to 13 billion parameters. And they really see that as far as comparing the accuracy of performance of like a pass at K, or evaluated, pass at K for code completion, they really only start seeing an improvement of performance using this multi-token prediction architecture once the number of parameters of your models get to be larger, as opposed to just using a single model. So that's something to keep in mind, because like multi-token prediction is not new. In some sense, like the engineering feat is like the engineering feat is not new, that they did in this. What is new as far as the engineering feat goes is that they're using much larger models than what people have used in the past when they introduced the idea of multi-token prediction. And so they do verify this, and they do verify that the gains are quite exponential when you increase the size of your models. The second result is they do show that with this decoding scheme, with this type of like parallel decoding scheme, they can get faster performance. They measured it as like a speed of 3 times on code and 2.8 or 2.7 times on text as far as decoding speed. So that means you can speed up your inference by that. So that gets, again, like, how you optimize everything, like with like this like parallel decoding procedure gets into a lot of the nitty gritty. So it's worth delving a little bit more into it. They don't in this paper, and so that's why I'm going to drop the other 2 papers about parallel decoding procedures in the chat so that you guys can look at that in more detail. And right. So another thing that they point out, and this is where the tokenizer problem is like that I brought up at the very beginning is important, is this idea about multi-byte prediction. So in order to be able to really effectively study whether they're doing like how well this model works, as far as like, so in order to be able to study this problem about like, like the local versus like a larger size of like, understanding of, I'll use the word understanding of the text, they look at a tokenization at the byte level. So at this part, they're still looking at code, but they're tokenizing the code on a byte level. So effectively like, like character by character. And what they're showing is that when you're looking at things at the byte level, and the reason why this is important is because you have less, so when you're looking at, like sub-word or word level, right? Like the human language and even coding language has more structure already inherent in it. So it skews your probability distribution more. So you have a little bit more randomization as far as, when you're looking at things at the byte level. This is also why people don't use byte level tokenization. But when you do byte level tokenization, what they show is that the performance increase by doing multi-token prediction, as opposed to just single token prediction at the byte level, it improves, at very drastic rates that you're able to solve 67% more problems at the pass at 1 and more problems at pass at and 20% more problems on HumanEval at pass at 1. I think they don't. Do they have a figure for this one? I think they don't have a figure for this one. Right. And so this experiment over here in section 3.3 that they do, this is the one that is the most key that they have as far as demonstrating that this method is able to learn larger than just very, very local structures. So that you really are not just doing like next token prediction. You're really not just doing the same type of like local patterns when you're training your models in this way. That you're actually learning something that's at a larger chunk level. I think that's very neat. And of course, like you see the performance increases in other structured pieces of data as well. When you're looking at not just like byte level tokenization. So it's maybe like a first step at actually understanding things that LLMs are very, very bad at, such as like understanding the ways that you link together different words. So not just an approximation of like, say, semantics, grammatical structure, most likely next sentence just based on the human vernacular, but actually maybe like a first step towards, and this is like a really baby step, but maybe a first step towards actually having the model encode and learn things like causality, sequentiality, all of those types of things like that are actually necessary in our way of thinking as humans. Of course, it doesn't encode it like very directly, but it feels to me like it's like a very baby first step towards it. That particular experiment. The searching for the optimal N. So just like when we talk about like tokenizers, right? Like when we talk about tokenizers, there's kind of an optimal size that we want to tokenize things. Having tokenizers to be too large is bad. Having tokenizers to be too small is bad. And so very similarly over here, as far as the parallel heads that you're going to be computing on, there's kind of an optimal head. So they found that I think when you're using byte level tokenizers, they really find that almost consistently 8 parallel heads work the best. When you're using larger tokenizers, then it varies based on the exact text, the exact nature of your data. So that they note that warrants a little bit more study to figure out what are like the optimum number of heads, but somewhere around 4, which is why they also show the picture with 4, tends to work the best. Another question that you can ask is, what happens? How is this different from training for multiple epochs? Because if you train a transformer model and then you train it for another epoch, then you have the information from, like you have kind of that, like, the information from, like you have kind of like, like that kind of like circular type of information that you get from like chunking the text into lengths of n. And they find that even then, even when they train across multiple epochs, the multi-head attention works better. But performance, like, the gap between like the performance, like the performance gains become less. But you still don't fill in the gap. There's still going to be a gap that is not filled. The fine-tuning result is particularly interesting. So for fine-tuning, they do 3 different types of fine-tuning experiments. One is when they're looking at just a vanilla transformer, and they're just fine-tuning the vanilla transformer. That's the red line. The green line is when they're using this multi-head approach, and they're fine-tuning each of the heads based on how they're training. And that's the green line. And they do see some improvements, but the number of improvements kind of decrease. They kind of decrease over, yeah, they kind of decrease as K increases. K is past at K. But what's very interesting, and this, they don't explain this, like why they think this is, and I also don't have an explanation for this, is that if they use this multi-head approach, but then they fine-tune the first head, like the way that you would fine-tune just a normal transformer, that consistently has an increase of performance. So that's very interesting. I mean, the first head is kind of the dominant head. So that might explain some of it. It kind of directs the other heads in the way that, you know, we do decoding, but yeah, that's something that I think warrants more study, and I think they mentioned that as well. And then right. And then the last thing that they study, so up until this point, most of what they studied was on code. And so how does this also perform on natural language? Code is much more structured. And this is where there's like some very nice philosophical thoughts that they offer later on in the paper. So when you're looking at natural language and when you're doing the type of benchmarking, as far as like, you know, predicting a multiple choice response, they actually do not see performance increases. They see performance decreases. What they claim, and what I also completely agree with, working in this field, is that these benchmarks are very much not the way that LLMs are actually working in real life, that they're very artificial. And so they try to change tasks to be like summarization tasks. And they also try to change the natural language to be mathematics, so mathematical reasoning. And what they find is that for both, so as far as like multiple choice reasoning on many of like the standard benchmarks, you do see a decrease in performance. But then when you do summarization tasks, and how you measure summarization tasks using a Rouge-L metric, you do see an improvement in performance. And when you're looking at its performance on mathematics, does it have the performance only in the, all metrics can be found in Appendix H? Okay, the performance on mathematics is only in the appendix, I guess. I remember how the figure that I'm looking for, oh, this is the figure that I'm looking for. This is, I liked this one. This one's very interesting. Okay, it's a little bit complex to explain the figure. Well, I'll save it for Q&A if you guys want me to go into to explaining some of these figures. But the high level over here is that for mathematical reasoning, where you do have a clear answer, but you arrive at the clear answer by mathematical reasoning. So it's different from just selecting a multiple choice. It's different from like a knowledge-based response, and it's different from like a truthfulness type of response or a language recognition type of response. So when you do have something that's like a structured thing, like mathematical reasoning, which arrives then at a final answer to the question, which can be easily then extracted, also different from multiple choice, right? Because you have a so-called like, correct answer for like a math question, but it's not selecting out of like A, B, C, D. And so when you have, and then when you check for accuracy on the final answer that it arrives at, it improves in performance. And so what this seems to indicate, what many of these results seem to indicate, especially the high performance on code and the high performance on math, is that this is very, that to me is like another indication that this is like the first baby step that we are getting to actually be able to start recognizing more of those like, things like sequential understandings of like, language. So again, not just like, like the human vernacular, but something that's like more sequential. Something that's more structured, and something that's more rigid. All right, I'll end over here. there's so many more things in this paper and so many figures to unpack. And all of these experiments, every single one of these are quite elaborate, and they put a lot of detail in there, which is incredible in this paper. But I will end over here. I'm going to stop recording, and I'll open this up to QA, and I'll be around for maybe like another half hour, as I usually am, and I'm happy to chat about anything else and touch deeper into any part of the paper.